Welcome back, my dear students. Have you ever wondered why does a phone charger have a capacitor? Or what's the difference between a capacitor and a battery? So in today's video, we will try to find out the answers to each one of these. Let's start. So we have something known as capacitance. What exactly is capacitance? So capacitance is the ability of a conductor to store charge. Now suppose you take in a conductor and you apply a potential difference. Now the amount of charge that the conductor will get will be directly proportional to the potential difference that you apply. So greater the potential difference you apply, greater would be the charge that your capacitor will hold. Now, since these two are proportional, to remove in the proportionality sign and to change it into an equality, we will have to introduce a constant. And this constant C over here is none other than the capacitance. So C here represents capacitance, but because it is a constant in this particular equation, therefore it does not depend on the charge, that's Q, or the voltage, that's V, the potential difference. Now, the SI unit to measure capacitance is farads. It's represented by a capital F. Charge we will measure in coulombs, represented by a capital C, and potential difference would be measured in volts, represented by V. So I can very easily say that 1 farad is actually 1 coulomb by 1 volt, or we can also say that farad is equal to coulomb volt inverse. Now over here, since I already told you that your capacitance does not depend on your charge or your potential difference, then on what does the capacitance actually depend? Capacitance depends on the shape and size of the conductor. It depends on the shape and the size of the conductor. Also, it does not depend on the material of the conductor, but yes, it depends on the nature of the medium in which we keep the conductor. So if it's a copper plate, if it's a aluminium plate, it does not depend on that, but in what medium do you keep your capacitor, that's what affects it. Like if it is air, or if you have put in some other medium in between, there could be wood, there could be glass, anything. Okay, so the medium affects it, but the material of the conductor does not affect it. Now 1 farad is actually quite big a unit for capacitance, so sometimes we also use smaller units like a microfarad. A microfarad would be like 10 to the power minus 6 farads, and we also use a picofarad, and 1 picofarad would be approximately 10 to the power minus 12 farads. So these two you should definitely learn, because many a times in the CBSE board exams, while we will give you the capacitance values, there's a very high chance that we give you the capacitor value or the capacitance value in microfarads or picofarads. So this is an important conversion that you should learn definitely for your board exams. Now, capacitors can be of different shapes and sizes. You can have spherical capacitors, you can have the parallel plate capacitors, and there are some other possibilities as well. But in today's video, our main focus would be on the parallel plate capacitor, because that's what is required from your CBSE point of view. So let's quickly jump onto the parallel plate capacitor. So parallel plate capacitors, what exactly are these? As you can see here in the diagram, I have two parallel plates. Both of these are conducting, and if I give a charge of plus Q to this plate A, a minus Q charge would be induced on the left side of this plate B, and a plus Q would be induced on the right side of plate B. But then this plate B's right side has been earthed. Now because it has been earthed, therefore the electrons will come and neutralize this plus Q charge, and hence the right side will no longer have any charge. And in turn, what would happen is that this negative Q charge will spread out on the whole plate B. So in other terms, my plate A is positively charged and plate B is negatively charged. Because of this charge, there would be some electric field that would be existing between these two plates. So there's an electric field between these two conducting plates. Now, if I talk about this electric field, then this electric field would be equal to the potential difference that has been applied to the plates by D, where D represents the distance between the two conducting plates. I can rearrange this equation to have V as equal to ED. So my potential difference is electric field times the distance between the two plates. Now further, if I assume that sigma is the surface charge density. Surface charge density means the charge per unit area. So sigma is basically Q by A, where Q is the charge and A is the area. And I know that V is equal to ED, right? And for the electric field that is there in between these two plates, we know that the electric field would be sigma by epsilon naught. So sigma by epsilon naught is my electric field and D remains the way it is. So my potential can be written as sigma by epsilon naught. Further, since my sigma is Q by A, therefore I can write this potential as, I can substitute the value of sigma here. So this would be Q by epsilon naught into A and this is into D. So my potential difference is charge times the distance between the plates by absolute permittivity of free space times the area. Now further, I know that my C is going to be equal to Q by V. So I can substitute this value of V that I have derived. So I'll have Q by V would be written as QD times epsilon naught A. So Q and Q get cancelled and from here my capacitance comes out to be epsilon naught A by D. This is the actual formula to calculate capacitance. See, you can calculate capacitance using the Q by V formula as well. But from this formula, we actually conclude certain things. What are those certain things? Firstly, my capacitance is directly proportional to the area of the plates. That means bigger the area of the plates, more would be the capacitance. Secondly, the capacitance is inversely proportional to the distance between the two plates. So greater the distance, lesser the capacitance. From these two things, we can actually conclude that capacitance depends on the shape and size of the conductor. And that is exactly what I had told you before. Fine. So I hope you understand this. And if you have any questions, then please leave in the comment box. I will try to answer them. Now, whenever we are talking about the parallel plate capacitor, it's very obvious and it's something that's required also that we talk about the dielectric when we are talking about the capacitor. So in between this capacitor, in between these two plates of the capacitor, there is just air, there's nothing else, or you could say that there's vacuum. But I can fill these plates with a dielectric. So I'm going to take a general situation where I assume that the parallel plate capacitor is partially filled with a dielectric. Okay, this is again something very important which you should know. So I had this capacitor, A and B are the two conducting plates and the distance between these two plates is small d, and I have inserted a dielectric slab of dielectric constant capital K. By doing that, you can see that there is this T space out of D, which was the total spacing between the plates. T has been occupied by this dielectric slab. Now, what happens when I put this dielectric slab over here? That is something that we will try to understand. See, initially on the previous slide, I had derived my initial or you can say C naught as the initial capacitance, which was epsilon naught A by D. So this is the capacitance when there is no dielectric present. Okay, and now we will see that how the dielectric affects various factors here and what difference would it bring to the capacitance. So originally my electric field was E naught. So what was E naught? It is the original electric field, or you can say that it is the electric field without the dielectric. Now, after I put in the dielectric, the electric field changes to E. So what is E? It is the electric field with the dielectric. Now, what is the difference between the two? E is going to be less than E naught. Why? Because the dielectric gets polarized. So due to the polarization of the dielectric, my E, this electric field, see E naught was original, and from this I have to subtract the polarization that has happened there, and therefore my E will be less than E naught. Why? You can see that if you subtract something from it, obviously it would become lesser. So E naught is greater than E. Now, if I want to write the potential difference here, so potential difference, earlier also we wrote it as electric field times the distance. Now, in the part here which is just having air, for that the electric field you already know would just be E naught. So E naught is the electric field in the part where there is no dielectric, and the distance for that one would just be D minus T. D was the total distance out of which T has been covered by the dielectric. And the electric field, because of the dielectric or with the dielectric, has become E, and the distance for which the dielectric is present is T. So my potential difference can be written as E naught into D minus T plus ET. Further, from the definition of dielectric, I also know that my E naught by E is nothing but equal to the dielectric constant K. Therefore, I can rearrange this to get my E as E naught by K. Now let's substitute this value of E over here in the potential difference equation. So my V would be equal to E naught into D minus T plus E naught by K times T. I can further take E naught common over here, and I would be left with, I have D, I have T, and I would have T by K. So this one here is my final expression for the potential difference. Further, because I know that my E naught, the original electric field, was sigma by epsilon naught, or you could say it was Q by A epsilon naught. So let's substitute this value of E naught here. So I'll have Q by epsilon naught A into D minus T plus T by K. So that is my final potential. Now I can also write in the value of my capacitance. So capacitance here would simply be equal to Q by V. So this is basically the new capacitance with the dielectric. So I am doing Q by Q into epsilon naught A, and this whole thing goes into the denominator. So I would have D minus T plus T by K. Now this Q and Q get cancelled. So from here my new capacitance comes out to be epsilon naught A by D minus T plus T by K. If you want to simplify this further, you can take D minus T common, and that would result in, so C would be equal to epsilon naught A by, if I take D minus T common over here, then inside I would be left with 1 plus, sorry, if I take D minus T common, then I'll be left with 1 minus 1 by K. So you could also write it like this. So this is my final expression. Now suppose we can take in a special case here. Let's say that the whole space between the capacitors, or between the two plates of the capacitor, was filled with the dielectric. So suppose my T was equal to D. Now if you substitute T as equal to D, then the capacitance comes out to be, this K will go to the top, so you will have K times epsilon naught A by D if it was fully filled with the dielectric. So if you compare this equation, like let's call it equation 2 and equation 1, you can very easily see that the new capacitance is K times the original capacitance. So basically, if you fill the capacitor with the dielectric, the capacitance becomes K times. That is how the dielectric affects the capacitance of a capacitor. Clear? Perfect. Now further, so we know almost everything about the capacitor now. Now let's start talking about the grouping of capacitors, where we are actually going to talk about how can we arrange these capacitors in series and in parallel? So first let's talk about our series capacitors. So now when you connect the capacitors in series, each capacitor gets the same charge. So in series, each capacitor gets same charge. So you can see the capacitor 1 has a charge of plus Q, on the other plate it's minus Q. Capacitor 2 also has plus Q, minus Q. Capacitor 3 also has plus Q and minus Q. Also, in a series circuit, the potential or the potential difference gets divided. So my potential of V has got divided into V1 plus V2 plus V3. Now over here, since they all have the same charge, therefore I can say that V1 would be equal to, for V1 I can simply say that it would be Q by C1, V2 would be equal to Q by C2, and V3 would be equal to Q by C3. This is from the basic definition of the capacitance, that Q is equal to CV equation. Let's substitute these here. So my V would be written as Q by C1 plus Q by C2 plus Q by C3. And this can be further written as, if I take charge as common, so I'll have 1 by C1 plus 1 by C2 plus 1 by C3. And now this V is actually nothing but the total charge by the equivalent capacitance. So this is Q into 1 by C1 plus 1 by C2 plus 1 by C3. Now if I cancel both the charges, then from here I can say that 1 by C equivalent, or the equivalent capacitance in a series circuit, is 1 by C1 plus 1 by C2 plus 1 by C3. This derivation, although it's pretty small, but it's an important one as well. Also, the final expression is equally important. The only two things to be kept in mind while deriving this is that each capacitor will have the same charge in series and the potential definitely will get divided. Further, let's move on to the capacitors that are connected in parallel. So now over here I have C1, C2 and C3 which are connected in parallel. Now in a parallel circuit, firstly, each capacitor will have the same potential difference because they are connected between the same 2 points. So each capacitor, that is C1, C2, C3, has the same potential difference V. Also, over here the charge gets divided, or you can say that the charge splits up. So the total charge, if I assume it to be Q, would be the sum of Q1 plus Q2 plus Q3. Now from the circuit itself, I can say that Q1 would be equal to C1V. Your Q2 would be equal to C2V and your Q3 would be equal to C3V. That is simply because each of them has the same potential difference. Let's substitute that here. So my Q would be equal to C1V plus C2V plus C3V. And now I can take my V common. So I'll have C1 plus C2 plus C3. Now Q is nothing but the total charge, which can be written as C equivalent into V. So C equivalent into V is V times C1 plus C2 plus C3. So potential can get cancelled on both the sides and your C equivalent is C1 plus C2 plus C3. So in a parallel circuit, we simply add in the capacitances, and in a series circuit, we take in the reciprocal. Now, one thing for you to notice here is that here, the total capacitance of the circuit will be higher or will be greater than the individual capacitances. So it would be greater than the individual capacitances. So this is something again important. Whereas if you connect them in series, then the final capacitance of the system would be less than the individual capacitances. Okay, so I hope this is clear. Now moving on further ahead, let's start talking about the energy that is stored inside a capacitor. Now see, whenever we are charging a capacitor, obviously you will apply a potential difference, which is definitely provided by the battery. So we simply say that there is work done by the battery. There is work done by the battery in order to charge the capacitor. Now this work that is done by the battery in order to charge the capacitor will be stored in the form of electrical energy. You can say it is stored in the form of electric field or electrical energy inside the capacitor. And it will definitely use this energy whenever you are using your capacitor. So in your mobile phones, when I started this video, I told you that your mobile phone charger has a capacitor. That is simply to store in the electrical energy. Further, now if I talk about the work that is done, in charging the capacitor, then how would we write that? Now we already know that my Q would be equal to CV. And if I talk about the work done in bringing a small amount of charge dq from the battery to the capacitor, so dw would be equal to v dq. Now I will have to integrate both the sides in order to get the total work done. Okay, so the dw would become w, and over here, see, v is a function of q, so I can replace v by q by c. And further, I know that the amount of charge is what we are integrating. So we are integrating with respect to dq. So c is a constant here since it does not depend on the charge. So 1 by c can come out, and you integrate this expression from 0 to q. So the work done can be written as 1 by c into. So when I integrate q, it would become q square by 2, and on substituting capital Q and 0, so I'll get q square by 2. So from here, my work done comes out to be q square by 2c, or in other terms, you can say that my potential energy that is stored inside the capacitor would be q square by 2c. Now, since I know that q can be written as cv, if you replace this with cv, you will have 1 by 2 cv square. So that's another form of the same formula. If I substitute v as q by c, then the same formula can be written as half into qv. So it's the same formula written in 3 different forms, depending on whether you want to write it in terms of charge and capacitance, or charge and potential difference, or charge and capacitance. Okay, so it simply depends. So this is simply the energy stored in a capacitor, and yes, you need to know this formula as well. Okay, so the derivations are pretty small, but then they will fetch you the marks that are required there. And not only that, they are straightforward. The final result of the derivations also needs to be learned. Now further moving on, now since we have learned everything about a capacitor, therefore we can start working on some PYQs. These are very recent PYQs, so you should surely know them. So let's start with the first one. So there's a parallel plate capacitor of capacitance C, as there is a dielectric slab between the plates. Now we charge it to a potential difference V by connecting it across a battery, and the battery is then disconnected. So the key word here is disconnected. Now if the dielectric slab is now withdrawn from the capacitor, how will the following be affected? So first let's talk about the capacitance of the capacitor. So now we will talk about the first part. C, the capacitance of the capacitor ideally has to decrease. So why does C decrease? So let us try and understand that. So if you remember, with the dielectric, the capacitance was K times the original capacitance. Now when you remove K, then the capacitance would decrease, because with the K it increases by K, and without the K it decreases. Why? Because actually the epsilon naught changes. When you do not have the capacitor, when you do not have the dielectric, that time your capacitance is epsilon naught A by D. But when you put in the capacitor, like when you put in the dielectric inside the capacitor, the epsilon increases, and so does the capacitance. So without it, your C has to decrease. Then For the B part, we have to find out the energy stored inside the capacitor. How would that change? See, just now we derived the formula that my energy is equal to Q square by 2C. Now the thing is that even if you remove the battery, even if you remove the dielectric, the charge remains constant. So because the charge remained constant throughout of this, therefore you can say that your energy is inversely proportional to C. So since my C is decreasing, therefore my energy has to increase. So the energy stored inside the capacitor increases. Now for the C part, talking about the potential difference between the plates, now we have V is equal to Q by C. So now I already know that my charge is again constant. So you can see that V is inversely proportional to C. So since my C decreases, the potential has to increase. And therefore, the potential difference between the plates also increases. So potential difference between the plates also increases. So this is our question. It's a very easy, straightforward question, but this has been there in the board exam for 2026, and similar questions have been asked in the past as well. So do not forget to revise this question before your final exams. We'll do another question over here. So let's read the question. There are two parallel plate capacitors X and Y, and they are connected in series to a 6-volt battery, and they have the same plate area, same plate separation, but capacitor X has air and capacitor Y contains a dielectric of dielectric constant 4. We have to find the capacitance of X and Y if the equivalent capacitance of the combination of X and Y is 4. So I know that the equivalent capacitance here is 4 microfarads. And if I assume that the capacitance of Cx is C, then I know that the capacitance of Cy would be K times C. So that means it would be 4 times C, right? Because there's a dielectric constant. So keeping these two things in mind, we will directly substitute in the formula that we just derived for the equivalent capacitance in a series circuit. So 1 by C equivalent is going to be equal to 1 by Cx plus 1 by Cy. So let's quickly substitute. I have 1 by 4 microfarads. This is going to be equal to 1 by C plus 1 by 4C. If you quickly simplify this can be written as, so this is 4 plus 1 by 4C. So you can quickly rearrange this. So you will have 4C equal to 5 into 4, that's 20, or your C comes out to be 5 microfarads. So your C, which is same as your Cx, is 5 microfarads, and your Cy, which is 4 times C, would be 4 times 5, that is 20 microfarads. So I have gotten the values of the Cx and the Cy. Now I want to figure out the potential difference between the two plates over here for the two capacitors, that is X and Y both. So for that, so if you want to find out the potential difference across X, okay, then for that I will first have to find out my charge, right? So I have to do Q by Cx. To find out the charge, I can simply take in that for the total surface. So this charge, or the total charge on the whole circuit, would be C equivalent times V, which is, the C equivalent was given to us as 4 microfarads, and the potential difference is 6. So I get this as 24 microcoulombs. Why micro? Because the capacitance was in microcoulombs as well. Sorry, capacitance was in microfarads as well. So my Q comes out to be 24. My Cx is 5. So 24 by 5, that gives me a total of 4.8 volts. Therefore, the potential difference across the capacitor X is 4.8 volts. Now for Vy, again, the charge is going to be the same because that's a series circuit. The charge is 24 microcoulombs, and for my Cy, that's 20. So 24 divided by 20 gives me 1.2 volts. So I have my Vx, I have my Vy, and I have the capacitances. So my question is solved. Again, an easy question. If you have studied capacitors thoroughly, then you should not get stuck on questions like this. I hope you understood capacitors and capacitance from this video. And if you did and if you enjoyed the video, then please subscribe to my channel, and I hope to see you next Thursday again. Thank you.